Hello everyone, my name is Komasinyolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, welcome to another video under the section of functions. Okay, so we are still looking at functions, but we are in particular looking at the nature of roots. Okay, I thought it is necessary for me to explain the nature of roots, although this is grade 11 content. I will explain it because they like to ask it in grade 12 past exam papers. Okay, so in exam papers. So let us jump right into it. The nature of roots. Firstly, what are roots? Before we actually look at their nature, what are they? What are roots? What are these things that we call roots? Okay, so if you have a quadratic equation, let's say you've got a quadratic equation y, you've got a quadratic equation y is equal to ax squared plus bx plus c. Okay, this is one of our standard forms of our quadratic equation. You will know it from experience from our past videos and from other questions that you would have solved in the past. Okay, so this is a quadratic equation. Right, now this quadratic equation, if you plot it in a graph, might look something like this. If you plot it on your Cartesian plane, it might look something like this. It might look it might look a number of different ways, right? This is just one example of what it might look like. If you look at this quadratic graph that I've sketched here, it has different y values for each x values. So if I've got an x value there, right, and I draw a line towards the graph, it has a corresponding y value there, right? And this is the case for all the x values, right? So for every x value, there is a y value. Okay, so this is basically, you know, all of this about your quadratic graph. Right, now, if I draw it out again, if I draw out that graph again, okay, in my Cartesian plane, there's my Cartesian plane there, there's my Cartesian plane there, and I draw it. Doesn't matter how I draw it. Even if I draw it like that, that's fine. Doesn't matter where I draw it, even if it's like this. Okay, it's another quadratic function. If I draw it out like that, you will notice that at those points there where the graph intersects the x-axis, at those points there where the graph intersects the x-axis, the value of your y there is, the value of your y is 0. Okay, so that's basically your x-intercepts. So the red points there, the points that I've circled in red are your x-intercepts. The x-intercepts are the values of x for which your y is equal to 0. Okay, so your roots are those values. So your roots are essentially your x-intercepts of your quadratic function. So these are your roots. Okay, so these are your roots. Those x values are your roots. So your roots are actually your x-intercepts of your quadratic graph. Your x-intercepts of your quadratic graph. Okay, those are your roots. Okay, so in grade 11 and grade 12, when we're talking about the nature of roots, we're basically talking about the x-intercepts of your quadratic function. That's all that we're talking about. It doesn't get any more complicated than that. Okay, that's it. It's your x-intercepts of your quadratic function. Now, if I draw out a different graph, right, I'm going to keep drawing them out to hammer this point home. Okay, if I draw it out like that, if I draw out your graph like that, let me try to draw it a bit more carefully, like that. Okay, the x-intercept is at that point there, right? So then the x-intercept at that point will be your root. Okay, if I draw out your graph like this, if I draw your graph out like that, your x-intercepts are there and there. So those are your roots. Okay, so those are your roots. Those are your roots. It's your x-intercepts. Now, if I draw a graph that looks like this, if I draw a graph that looks like this, if I draw a graph that looks like that, a quadratic graph that looks like that, you will agree with me that this graph does not have x-intercepts, right? There is no x-intercept because this graph does not cut the x-intercept at any point. So there is no value of x for which y is equal to 0. There isn't. Y is equal to 0 is at that point there on your x-intercept. So the graph does not hit the Cartesian plane at y is equal to 0. So there is no x-intercept, meaning that there are no roots. There are no roots for this graph here. There are no roots. There are 0 roots. Or in other words, if you want to put it in a different way, you could say the roots for this graph are unreal. Okay? There are no real roots, because you're looking at this graph, there are no real roots, right? There are no real roots. So if anybody comes to you and says that this graph that they've sketched out here, this graph that I've sketched out here has roots, you'll just look at them and say, nah, those roots then they're not real, because I can't see them. They can't be real. So those roots have to be unreal. There are no roots, or there are unreal roots. You can just say unreal. So unreal roots is just a fancy way of saying that the graph does not intersect your x-axis. That's all. Okay, so that's what roots are. Roots are, if there's anything that I want you to take away from this video, it's that the roots of a quadratic function are the x-intercepts of that quadratic function. Okay, and if that quadratic function does not have x-intercepts, then that quadratic function does not have roots. Okay, so let's look at this in a bit more detail. So let's say, right, you've got your graph. Okay, on your Cartesian plane, you've got your graph that looks something like that. Okay, and this graph has an equation. Okay, so this graph has an equation. It has some equation. Now that equation is y is equal to ax squared plus bx plus c, because it is a quadratic function. How do you find those x-intercepts of that graph? How do you go about finding the x-intercepts of a quadratic function or a quadratic expression? How do you find the values of x? How do you find these two values of x for which your y is equal to 0? Well, you will agree with me, and you will know from grade 11 and grade 10 that you can use the quadratic formula. Okay, so the quadratic formula, where you can find x1 and x2, is equal to minus b plus minus the square root of b squared minus 4ac all over 2a. You use this equation to find the x-intercepts of your quadratic function. That is all you use this equation for. Now, if you use this equation to find the x-intercepts, if you use this equation to find the x-intercepts of your quadratic function, then you will agree with me that it follows that you use this equation to find the roots of your quadratic function, right? If you use this equation to find the x-intercepts of your quadratic function, and your x-intercepts are the roots of your quadratic function, then it follows that you use this expression to find the roots of your quadratic function, right? Your roots are your x-intercepts, and if you use this to find your x-intercepts, then you use this to find your roots. Okay, I hope that makes sense. So that's what your roots are, and that's what this video lesson is about. It's basically looking at the nature of roots now. Okay, now we want to look at the nature of your roots. Now that we've actually seen what roots are, we can actually start looking at the nature of those roots. Now, your roots can have certain characteristics. Okay, so I'm just going to draw out a Cartesian plane. I'm going to keep drawing out a Cartesian plane to explain. Your roots can have certain characteristics. If I draw out, and I explained this early, if I draw a graph that looks like that, this is a quadratic function. It's down here. Okay, if I draw it out like that, you will agree with me that the nature of the roots for this, graph that I've drawn out here are non-real, right? They are non-real. Why are they non-real? Because this graph does not intersect with the x-axis. So the nature of these roots are non-real. They are unreal, right? They are unreal. This is one type of this is an aspect of the nature of the roots that we're going to be dealing with. They are non-real, they don't exist. Okay, now we can also have another nature of these roots that we can deal with. So let's say I've got a graph that looks like that, right? I've got a graph that looks like that. Well, you will agree with me that the x value here, the x value there, and the x value there are not the same, but they are real, right? They are real because they exist. They are real because this graph goes through the x axis. Because this graph intersects the x-axis, we have values of x there for which y is equal to 0. We actually have values of x for which y is equal to 0. So they are real because we've got this graph intersecting the x-axis. So these ones we know for a fact that they are real, right? These ones are real, and then here we've got non-real roots. Here these ones are real. But not only are these ones real because they intersect your x-axis, they are also not equal, right? They are real and unequal. You will agree with me that those two x values are not equal. These two x values, this x value there and that x value there, are not equal because they're at different locations of the x-axis. So this might be 1, 2, 3, 4, 5, 6, 7, whatever. So if this is 6 and this is 4 or 3, whatever, then they're not equal. 4 and 3 and 6 are not equal. So, okay, so these roots are real and unequal. Why am I saying they are unequal? Because they're not equal. You can actually see that those x-intercepts, they are not equal, but they are real. Why am I saying they're real? Because they cut through the x-axis. Okay, so we can have another type of a different nature of your roots, right? Remember, just substitute the word root with x-intercept because they're the same thing. Your roots are your x-intercepts. Okay, now if I have a graph that looks like, I'm going to try to draw this accurately. Like, I just want to touch my x-axis. Okay, like that. Right. You will agree with me that if you look, when you're looking at this graph, right? Looking at this graph, you only have one x value there where the graph touches the x-axis. Just one x value. So that's just one x value. Okay, one x value. Now, it's not the number 1. The x value is not equal to 1. It's just one x value. Okay, so doesn't matter what the graph looks like. It could look like that as well. It has to be a quadratic, and it just touches your x-axis there. Okay, so one value touches your x-axis. What can you tell me about the nature of this root? Well, it is equal, right? We know that we have two roots for a quadratic expression. We've got two roots for this quadratic expression, meaning we've got two x-intercepts. But in this case, you can see that we've got one x-intercept, right? So if for a quadratic function we need two x-intercepts, we need two roots, but in this case you only see one, then it means we've got two roots, but those two roots are made up of just one x value, right? So the roots of this graph, as I've sketched it here, are equal. They are real. Remember, they are real. Why are they real? They are real because they cut through the x-intercept. They are real because they cut through the x-intercept, and they are equal. For this particular graph, they are equal because it's just one x value making up two roots. Well, this one x value there, this one x value is making up two roots. Okay, and you know that in order for you to be able to find these roots, you can use the quadratic formula, this quadratic formula here, because you're basically just finding the x-intercepts. Okay, so that's what we're talking about when we're talking about roots. Okay, we're talking about the x-intercepts of a quadratic formula. Of a quadratic equation. Okay, so you've got the different natures of roots, and graphically, this is what it means. I'm going to repeat myself again. Non-real roots are for quadratic functions that do not touch the x-intercept. Non-real roots are for quadratic functions that do not touch the x-intercept. Real roots that are unequal are for quadratic functions that go through the x-intercept, but those two roots are not equal. So you've got two x-intercepts that are not equal, and you can clearly see from this graph, right? And then for real roots that are equal, you've got your graph looking like that, where it touches the x-intercept at one point or at just one location. Okay, so that is the nature of roots. Now, in how do you establish whether you see we've just established graphically using graphs whether roots are real or unequal or non-real or actually equal. Okay, so we've just established using graphs. But how do you establish that mathematically? Okay, so I find that it's easy now to understand what is going on mathematically if you understand what is happening graphically. If you understand the graphs, then the mathematics should be easy. Okay, so you agree with me that to find the x-intercepts of a quadratic equation, you use the quadratic formula. Okay, we covered that earlier on. B squared minus 4ac divided by 2a. Now, how do you establish whether your roots are real, non-real, equal, or unequal, or to take it a bit further, rational or irrational? Okay, so we're going to add that. I'm going to explain what that means as we progress further into this video. But how do you establish that mathematically? Okay, so you've got this thing here. This equation, this quadratic formula will help you find the actual value of your roots. So if you've got an equation, right? If you've got an equation, a quadratic equation, let's say y is equal to, let's say x squared plus 4x, say, plus 15. Plus 15, right? If I ask you to find the x-intercept of this equation, you could find it by factorizing, or you could find it by using the quadratic formula. I'm going to find it by using, firstly, I'm going to use both methods. Firstly, I'm going to factorize first, right? If I had to find the x-intercepts, I know that that's going to be x there, that's going to be x there. And I look for two values that when multiplied together are going to give me 15. Two values that when I multiply them together are going to give me 15, but when I add or subtract them, they're going to give me 4. What are those two values? Do I have those two values? Let's see. 5 times 3 is 15. Okay, just to make this easy, let's use 8 there, so that we have a nice number. Let's use 8 there. Okay, so then I'm going to use 5 and 3. Okay, so I just manipulated this example so that it works out nicely. So if I've got 5 and 3 there, then I know that for this equation, my x-intercepts are x is equal to minus 3 and x is equal to minus 5. Right, I just basically found my x-intercepts for this quadratic equation. You can look at a separate video of how to find x-intercepts, okay, the quadratic function equations that I prepared earlier on. So these are my x-intercepts, right? So these are my roots. These are my roots for this equation here. What does that mean? Well, if I were to sketch this equation, very quickly, what I would have is the following. I would have my Cartesian plane that looks like that. Then I would have 1, 2, 3, 4, 5. Minus 5 there. Then minus 3 here. Then 15 is my y-intercept. Okay, 15 is my y-intercept. Let's say 15 is there. And then my graph looks like that. Right, my graph looks like that. Those two values there, this value and that value, are my roots. These are my roots. Now, what can you tell me about these roots? Well, firstly, you will tell me that these roots are real. Okay, these roots are real. What else can you tell me? You can tell me that these roots are unequal. These roots are not equal. They are unequal. How do we know that they're real? Because they cut through the x-axis. How do I know that they're not equal? Well, because minus 5 and minus 3 are not equal, right? And they are your roots. So they're not equal. So you can clearly see that they're not equal. But how would you tell that mathematically? Well, let's use the Let's use the quadratic formula quickly. If you were to use the quadratic formula, you would say x1 and x2 because you've got two roots, so it's going to be x1 and 2. Then you're going to say minus b. What is b? b is 8, right? B is 8. So b is 8, a is 1, b is 8, c is 15. So b is 8. b is 8 plus or minus the square root of, we said b is 8, so that's going to be 8 squared minus 4. A is 1, and then 15 is c, all over 2a. 2 is 1. I mean, a is 1. Right, and then if you solve this, you're going to have minus 8. Then you're going to have plus or minus the square root of 64 minus 15. Okay, minus 15 times 4. Let me just say minus 4 times 15. I'm just substituting now. All over 2. Okay, then you're going to have minus 8 plus minus 64 minus 15 times 4 is 60. So that's going to be the square root of 4. Square root of 4 all over 2. Okay. All over 2. And then your two answers are going to be, so x1 is going to be minus 8. I'm just going to use the plus first on its own. So it's going to be minus 8 plus the square root of 4 divided by 2. So that's going to give you minus 8 plus 2. Right? Divided by 2. Then that's going to give you minus 6 divided by 2. That's going to give you minus 3. Okay, that's your first root. And then if you do the second one where I use the negative, it's going to be x2 is equal to minus 8 minus the square root of 4 divided by 2. That's going to give you minus 10 over 2. I'm just doing the math quickly. It's going to be minus 5. Okay, so I basically just wanted to show you, to remind you that the quadratic formula can be used to find the x-intercepts, and we just did that. Okay, so firstly we found our x-intercepts by factorizing here, and we got minus 3 and minus 5. Now we just used the quadratic formula and we got the same answers of minus 3 and minus 5. Okay, now it turns out, right, so remember what I said about the characteristics of these roots that we found here. They are real because they cut through the x-intercept, right? They cut through the x-intercept, and they are unequal. They are unequal because they're actually not equal. Minus 3 and minus 5 is not the same. They're not equal. Right, so it turns out that for non-real, not for non-real, let's look at what we're dealing with now. For real and equal roots, for real and equal roots, for real and equal roots, this expression here in the quadratic formula, this expression here in the quadratic formula, where's the quadratic formula? This little expression here, this little expression there, in order for our roots to be real and non-equal. Let's start off with the non-equal first, because this is the example that we are looking at. Real and unequal, right? This is the example that we just looked at. We just found roots that are real and unequal. For real and unequal roots, that expression in the quadratic formula, b squared minus 4ac, has to be greater than 0. Right, it has to be greater than 0. So let's just confirm if that is actually the case here. Right, for this example that we looked at, it has to be greater than 0. Remember that a is 1, b is 8, and c is 15. Let's see if this is actually greater than 0, because it turns out that that expression has to be greater than 0 in order for our roots to be real and unequal. Right, so if a, for our example, is 1, and b, for example, is 8, and c, for our example, is 15, And we've got this b squared minus 4 ac has to be greater than 0 for real and unequal roots. Let's see if this is actually the case. Okay, so what is our b? Our b is 8. Our b is 8 squared minus 4. Our a is 1 and our c is 15. Now, is this greater than 0? Is this greater than 0? Let's see. This is 64. 8 squared is 64. 4 times 1 times 15 is 60. And this gives you 4. And it does, in fact, turn out that 4 is greater than 0. So it is greater than 0. So our roots are real and unequal. And we've just seen that from our example. We've got those values of a, b, and c from the example that we were looking at, and we saw that we got real roots because they cut through the x-axis, and they are unequal because the roots that we got, the x-intercepts that we got, are not equal. Okay, they're not equal. So that's the nature. That's the first part of our nature of rule. Of our nature of roots, they are real and unequal. Now, what if we have real and equal roots? Let's come up with another example. What if we have real and equal roots? Well, let's say you've got y is equal to x squared plus 8x. I'm just gonna try to keep it close to the example that we used, and then plus 16, like that. If I ask you to find the x-intercept of this graph, how would you do it? You could use the quadratic formula, or you could factorize. Okay, you could factorize. Okay, I'm gonna use the quadratic formula quickly because that's what we're using. In this video, we've got x1 and x2 is equal to minus b squared minus 4. What am I doing? I'm lying. Minus b plus or minus, this is the quadratic formula. So that's going to be b squared minus 4 ac divided by 2a. Okay, so what is our minus b? What is b? B is 8. B is 8 plus or minus the square root of 8 squared minus 4. A is 1, C is 16, divided by 2 times 1. Remember, the whole point of the quadratic formula is to help us find the x-intercepts of our quadratic function. That's all that we're doing here. You could do the same thing by factorizing. Okay, so we've got minus 8 plus or minus the square root of 8 squared is 64 minus 4 times 16, it's 16, 32, 48, 64. Excuse me, that's going to be 64. So that's 64 minus 64, and that's divided by 2. If we simplify this further, what we have is minus 8 plus or minus the square root of 0 divided by 2. Square root of 0 divided by 2. Okay, so our x-intercepts in this case, you've got x1 being equal to minus 8. I'm going to start with the plus first. I'm going to use the plus first. That's minus 8 plus the square root of 0 divided by 2. That's going to be minus 4. Okay, what is x2? Well, x2 is equal to, now I'm going to use the minus, so it's minus 8 minus the square root of 0 divided by 2, and that is still minus 4. Well, surprise, surprise, you've got two values here that are the same. You've got two values here that are the same. In other words, you've got two values that are equal. Okay, so remember, these are your x-intercepts. Now, these x-intercepts are, they're two separate values. You can see they're two separate values, but they are the same. They are equal. So what does this tell you? This tells you that these are two real equal roots. Why do I say they're real and why do I say they're equal? Let me quickly sketch that and explain. So I've got my Cartesian plane. I have minus 4 at that point there because that's the x-intercept that I got, right? My graph does that. Let me just try to draw it a bit neater. Okay, my graph does that. Okay, the x-intercept is at -4, then the y-intercept is 16 because that's the y-intercept that I have here. That's my y-intercept there. Okay, so if you look at this graph there, how many roots does it have? It has 2 roots, but those 2 roots have the same value. They are -4. So these roots are equal. These roots are equal because it's just -4. It's 2 roots with the same equal value. And these roots are also real, right? These roots are real. Why am I saying they're real? Because the graph is touching the x-axis. All that has to happen for your equation or for your graph to have real roots is it has to touch the x-axis. That's all that has to happen. Okay, so now it turns out there's a condition mathematically for us to prove that an equation, a quadratic equation, has equal roots that are real. Okay, has equal roots that are real. What is that expression? Well, it turns out that that expression in the quadratic formula, that b squared minus 4ac, has to be equal to 0 in order for our roots to be real and equal. For our roots to be real and equal, that expression has to be equal to 0. Now, if you look at our example here, if I go back up there, while I was solving, I want you to notice something. Look at this. Look at this inside the square root. Look at that value inside the square root. That is 0. That is 0. And because that is 0, we got the same answer both times. We got -4 for x1, and for x2, we also got -4. And that is why our roots are equal and real. They're equal because -4 is equal to -4. They are real because our graph cuts through the x-axis. Okay, so that's why this condition has to be met. This condition has to be met in order for our roots to be real and equal. Okay, so I'm basically just explaining mathematically what I explained graphically using a graph. Okay, now let's try to look at another final example. Okay, so I think I'm going to cover a rational and irrational roots in a separate video because this video is going to become too long. But let's just cover unreal roots now. Let's just cover unreal roots. Remember what I said to you about unreal roots? It simply means that your graph does not have x-intercepts. Okay, your graph does not have x-intercepts. So let's see if I can try to come up with an example. Let's say you've got y is equal to x squared plus 8x. Let's see if I can come up with an example. -1. Okay. No. -1, 7. Okay, so this is an example. I'm going to stick with this example. This is the example that I'm coming up with. Right, now, this graph here will have to test. Let's say we're asked to find the x-intercepts of this graph. Okay, we're asked to find the x-intercepts of this graph. In other words, we are asked to find the roots of this graph. Okay, now if I asked you to sketch this graph quickly, you will agree with me that this graph, let me just try to draw this a bit neater. This graph will cut through the y-axis at that point at 17. Okay, it will cut through the y-axis at that point at 17, and the shape of this graph will be a smiley face because that is greater than a. I covered that in a separate video. Right, but does this graph have x-intercepts or does it not? Right, so in other words, does this graph do that? Or does this graph do that? Right? Or does this graph do that? Notice what I'm doing here. Does this graph have two x-intercepts, or does this graph have one x-intercept, or does this graph have no x-intercepts? Which one is it? Which one is it? Right? Because we know that if the purple applies, if the graph has two x-intercepts, then we've got two roots that are unequal, but they are real. If the red applies, then we've got a graph that has one root, that two roots that with the two roots that are equal, basically two roots that are equal and real. If the blue applies, then we have a graph that has non-real roots. How do we test if a graph has real roots or non-real roots? Well, it turns out that from that description there, that expression inside the square root, this expression b squared minus 4ac, this expression has to be less than 0 for your roots to be non-real. For your roots to be non-real, that expression has to be less than 0. Now, why is that the case? Why? Well, you will agree with me that the square root of a negative number is non-real, right? It's an unreal number. It's a non-real number. The square root of a negative number is non-real. So if it happens that we come across the square root of a negative somewhere, then we know that we're dealing with an unreal number. But if you look at the quadratic expression, the quadratic formula rather, if you look at the quadratic formula, you've got x1 and x2 is equal to minus b plus minus the square root of b squared minus 4ac all over 2a. Right. You will agree with me that that expression there, if that expression is negative, then I will have the square root of a negative number, because that expression is underneath the square root. That expression is underneath the square root. So if that expression is negative, then we'll end up with the square root of a negative number. If we end up with the square root of a negative number, then we will have an unreal answer, right? So x1 and x2 will be unreal, meaning that the quadratic function that was used in this quadratic formula will not have x-intercepts. Okay, so our example is as follows. Our example is y is equal to x squared. Remember we said plus 8x plus 17, right? If I substitute that into the quadratic equation, what I'll have is x1, x2 is equal to minus b. What is minus b? Minus b is 8, right? Plus or minus the square root of 8 squared minus 4. A is 1, C is 17. C is 17 divided by 2a. All divided by 2a, where a is 1. Okay, so what is that? Now, I don't have to solve this entire thing. Because I can already see that inside my square root there, I'm going to have a negative, right? So that's going to be, I'm just going to focus on the part inside the square root. What's going to happen? You've got 64, that's 8 squared, right? Minus, what's 17 times 4? 7 times 4 is 28. So that's going to be 28 plus 40. That's going to be 68. Okay, that's going to be 68. Now, 64 minus 68 is minus 4. Minus 4 is less than 0. So, minus 4 is negative, meaning that I've got the square root of minus 4. It's the square root of a negative number. If you take this and you punch this in your calculator, you'll get a math error or mathematics error. You'll get an error message, right? Because this is unreal. You can't have it. It's not a real number, right? It's not a real number. Since this is not a real number, we can confirm that, okay, this equation, because this is the equation that we used to solve our quadratic formula, this equation is going to be represented by the blue. not by the purple, not by the red. It's going to be represented by the blue. So your graph will look like the blue there. Okay, so your graph will look like the blue. It will be non-real. Non-real. Okay, it does not have real x-intercept values. It does not have x-intercepts. It's non-real. Okay, so in essence, what can you tell me about what we've just covered? Well, I will tell you what you should be able to tell me. Y is equal to ax squared plus bx plus c. The nature of your roots depend, okay? The nature of your roots. So whether your roots are real or non-real or equal or unequal, the nature of your roots depends on the values of A, B, and C. A, B, and C. They heavily depend on the values of A, B, and C. You will notice that I had 3 different equations that I used as an example. The first example that I used was y is equal to x squared plus 8x plus 15. Okay. The second example that I used was x squared plus 8x plus 16. Third example that I used was x squared plus 8x plus 17. Okay, and we noticed that for this first equation, let's do that. We noticed that for this first equation, we had real unequal roots. That's where our x-intercept was -3 and -5. That's where our graph looked like that. Our graph looked like that. Okay, for this one here, for the second one, we had real and equal roots. That's where our graph looked like that, where it just touched the x-intercept at one point. And for this one here, we had unreal or non-real roots. This is where your graph looked like that. Okay. Your graph basically did not touch your x-axis. Okay, so changing that value there changed the nature of your roots. But even if I were to change that value there, okay, I didn't do enough examples to demonstrate that, but even if I were to change that value there, that would affect the nature of your roots. Even if I were to change that value there, the a, it would change the nature of your roots. So for different values of a, b, and c, the nature of your roots would change. In other words, for different values of a, b, and c, you might have x-intercepts, you might not have x-intercepts. And if you have x-intercepts, they might be equal or they might not be equal. Okay, so that's basically what roots are, and that's the nature of your roots, and that's what all of this stuff means. Okay, so I think it helps to understand them graphically, and I think this is the best way for me, at least, to explain them. Okay, so we'll cover examples in separate videos. We'll maybe cover a past paper on a separate video. I might cover the past paper, or Kevin might cover the question. But as far as this video goes, this is what the nature of roots mean. Okay, till next time.